Hello fellow CNC nuts and welcome. In this episode we're going to take a look at how we can use our CAM software to produce the smoothest running G-code we can for our CNC machine. I'd like to start by thanking all of those who left comments on the last video, especially those of you who pointed out that you can't make Mach 3 run smoothly in exact stop mode. You guys were right and I was wrong, horribly wrong, when I said that I'd stop using constant velocity and move to exact stop motion only. I was wrong. I had to go back and reload some of my very old backups of Mach 3 and found to my surprise that I actually had been running them in constant velocity. I absolutely apologize to you guys. You were right, I was wrong. In Mach 3 you have to use constant velocity. Mach 3 exact stop is a turd. With that said, we're going to modify this video a little bit by including the Mach 3 settings for constant velocity. And hopefully we can get the best running machine we can out of it. Now in the last episode I showed how constant velocity can screw up your toolpaths by the simple demonstration here. My hexagonal shape basically turned into circles. That was done using default settings in Mach 3 and was done for demonstration purposes to show the effect that constant velocity has on a toolpath. Certainly when you've got it set up you will not get this bad an effect from your machine. Simply to demonstrate what constant velocity is doing. So the first thing I'm going to do is I'm going to take this flash drive, which has some fairly horrible G-code on it, direct from the CAM software, and run it in exact stop mode, and we'll see how it behaves. So this first demonstration is using the Masso CNC controller running in exact stop mode. And as you can see, it's running smoothly around the oval shape until it gets to here where it stops, drops the cutter further into the material and continues running around. Now I'm using this to demonstrate that not all exact stop motion control is the same. Machines that specialize in exact stop motion have far superior motion control than those that don't. So now we're going to run the exact same file in Mach 3 using exact stop. Mach 3 is set up with exactly the same parameters as my Masso, so we would expect to get the same results. If you have young children with you watching, I recommend they avert their eyes now. As you can see here, the motion is completely different. The machine moves and stops with each G-code instruction. So next I want to take a look at the G-code file we just ran and at our CAM software, because there's a couple of things we need to understand about G-code. So here we have a basic oval shape that I drew in a spire. If I select it and look at the nodes, you can see it's made up of 4 arcs. Now when we look at the G-code, we can see that the G-code is made up of a whole series of G1 moves. G1 is a straight line. So why is our oval output as a series of straight lines? It all comes down to the fact that while all circles or parts of circles are arcs, not all arcs are circles. A circle has a defined center point and a radius. An arc does not have a defined center point with corresponding radius. So this oval here is made up of what are known as Bezier curves. We could see them in our CAD software, 4 distinct nodes, and they were Bezier curves. They cannot be described in G-code because G-code only describes circular arcs. So in G-code there are 3 basic moves. We have the G1, which is a straight line. We have the G2, which is a clockwise circular arc, and we have the G3, which is a counterclockwise circular arc. So when it comes to outputting our oval shape into Gcode, what our CAM software does is it outputs a whole series of straight lines that make up our oval shape. The result is we can end up with over 1,000 tiny little lines making up that oval. So here we have our oval, and you can see the 4 quadrants that make it up, the 4 Bezier curves. And you know they're Bezier curves because they have these little pull tabs on each node that you can sort of move and push and pull. Now they are different from what we see on a circle. When we look at the nodes on a circle, there are these 4 nodes here, but in between are these center points here that we can push and pull like so, but we don't have those long drawn out tails like the Bezier curves. So I'm just going to get rid of the circle and we'll come back to our oval here. And what we want to do is we want to convert it using the Fit Curves to Selected Vector tool. So I've selected my oval and I can convert it to circular arcs, Bezier curves or straight lines. We of course want circular arcs, and here we can put in here our tolerance. The tolerance will define how much leeway we have on our oval. Now, of course it depends on what you're doing with your oval. If it's something decorative, then you can afford a bigger tolerance. If it's something that's mechanical, maybe some sort of a cam or something, you may require a much higher tolerance. I'm just going to leave it at 1/100th of a millimeter, or about just a bit less than 1/1000th of an inch. And I'm just going to hit preview, and you can see what it's doing here is it's going to create all these nodes around it, and each of these nodes will be a circular arc. I'm just going to go OK, and now if we select our oval and look at the nodes on it, here we can see our circular arcs. We know they're circular arcs because they have these little center points. So what we'll do now is we will output this here to Gcode and we'll see what it looks like. So here we have our new Gcode, and as you can see now it's output a whole lot of G3 moves. So it's going to be cut in a counterclockwise direction. But the interesting thing to note here is if we come down to the bottom of the file and just highlight the last character in it, we can see there are 129 lines of Gcode. When I look at the original file we had and highlight the last line, we can see there are 1054 lines of Gcode. So there is a big difference between using circular arcs and outputting it as a series of straight lines. The Gcode is a lot smaller, a lot more compact, a lot more efficient. Of course, that leaves the big question, will our new improved, more efficient, more compact Gcode run any better in Mach 3 now? Let's give it a try and see what happens. Okay, well, perversely that looked both better and worse at the same time. Where it was moving, it was definitely moving nice and smoothly, but it was punctuated by violent stops and starts. It was also moving faster than it was before as well. So this is now where we need to get rid of those stops and starts, and for that we need to introduce constant velocity. Setting up constant velocity in Mach 3 are relatively simple with only 4 parameters. We first go into config and general config. So the first one we need to look at is motion mode, and we just simply set that to constant velocity. The next one is the look ahead number of lines, and I'm going to change that to 200, which is the recommended value that ArcSoft, who create Mach 3, recommend. You can go up as high as 1000. Next we have here, I'm going to put a check in the constant velocity
distance tolerance, and I'm going to change that to 10 units. So because I'm running metric, that's 10 millimeters, but that 10 millimeters probably doesn't mean what you think it means. Lastly, we have stop constant velocity on angles greater than, and then you can specify the number of degrees. We'll come back to that one later. Right now we're going to click OK, and we're going to test whether 10 units is right for my machine. So I'm definitely hearing some hesitation as it moves from one arc to the next. So I don't believe we've got enough tolerance on there. So I'm going to go back into config, go into general config, and I'm just going to increase that just a little bit. It didn't sound too bad. I'm going to go out to 13. We'll just go OK, and we'll rerun our test. Okay, well, I'm still detecting a little bit of hesitation there. It just doesn't quite sound right, but we are very close. I think I'll just push this out, go into config, general config again. I'm just going to push this out to 15 units, and we'll give it another test and see what happens. Okay, well that sounds a lot better. It's now running smoothly, and I'm not hearing the hesitations as it moves from one Gcode arc to the next.
So is 15 the magic number? I don't really know. That is the starting point. Next time a file needs to be run on it, I would give it a run, do an ear cut, just have a listen. Does it sound right? Is it hesitant? Do I need to increase that CV number to 16, 17, 20? And I just keep doing that until I no longer had any problems with it, that it always sounded right. Why don't I cut what I'm doing? It's because listening will tell me what's going on. Do I have the hesitation? I'm looking for that lowest value that will remove the hesitation. That lowest value of tolerance will give me the best quality of cut that I can expect using constant velocity. So having gone to all the trouble of figuring out what that constant velocity distance tolerance is for my machine, what does it actually mean? Well, the 15 in my case is 15 units, 15 millimeters, because I'm running metric. But that doesn't mean I can come 15 millimeters away from my lines. What that means is from the end of the line, 15 millimeters before I get to the end of my line, I can start distorting the toolpath. So 15, if I'm traveling in this direction here, 15 millimeters from the end of my line there and there, I can start making curves so that I can keep my constant velocity. So I can come up here, and then I can start turning like this, and then keep moving. So I can only make those changes to the toolpath when I'm within the designated distance at the end of my line. So in the case of this 90-degree corner, I lose this much of my corner, and I end up with quite a pronounced curve. Now the error isn't so big on a corner that's got a much shallower angle. So 15 millimeters there and there, I can come up here, and then I can start turning like so. So I only miss just this little bit on the corner. So the shallower my angle, the less error there will be. But the good news is there is a way of reducing this error, if your machine will allow it. Now, if you remember the analogy of a car coming into a corner, if you want to go at a certain speed, you need to take that corner, you need to cut that corner a certain amount to get round it and keep that speed constant. Now what happens is, if my acceleration and deceleration is a lot higher, then I can get further into that corner, decelerating as I go, and then accelerate out of that corner. So higher acceleration will give me more accuracy. That means I should be able to reduce the tolerance value. So what I'm going to do now is I'm going to increase the acceleration on my stepper motors by a factor of 3, take them from 400 millimeters per second up to 1200. And then I'm going to decrease the tolerance from 15 down to 5. And if you remember, 10 sounded horrible, so 5 will as well. This will show us whether increased acceleration will allow us to decrease that error. I'll start by going into Config, Motor Tuning, and I'm going to increase the acceleration up to 1200 for the X and Y axis. Go OK, and then I'm going to go into Config, General Config, down here to our CV distance, tolerance distance, and just change that to 5. Let's give it a run and see how it goes. Okay, that result is excellent. Increasing the acceleration by a factor of 3 and decreasing the tolerance by a factor of 3, we still have that same nice smooth motion. So if your motors have high acceleration, they're going to work even better than ones with low acceleration. You're going to have that smaller error with your constant velocity. The final parameter we need to look at in constant velocity is the angle at which constant velocity turns off. So imagine if you are machining something like this here. If you want to go all the way up to that tip there, then you're going to need to turn the constant velocity off. If you don't, it's going to come up here and it may cut the corner like that. If you have better acceleration, it may come up as high as here and cut the corner like that. Depending on what you're machining, that may or may not be acceptable.
According to ArcSoft, who make Mach 3, the recommended value to enter into the stop constant velocity on angles greater than is 90 degrees.
Ultimately, what you decide to use as the cutoff angle for constant velocity is entirely up to you. If you are doing something that requires to keep those angles nice and sharp, then you may need to look at either changing the value or turning constant velocity off for that cut. Okay, so now that we've got our tolerance sorted and we've got our angle sorted, there's one more thing we can do to improve the smoothness of our machining. You noticed as we went around that oval, when the Z-axis dropped down to do the next cut around, there was a hesitation there. So now we're going to do a little bit of cam work magic and get rid of that problem as well.
So currently what happens is my cutter drops to a depth of 5 millimeters. It does one pass around the oval, it drops another 5 millimeters, does a second pass, and that's it. What we want to do is look at ramps. And there are two types of ramp we can use. We can use either a smooth ramp or a spiral ramp. So the spiral ramp will start here, and as it rotates around for the first pass, it will drop down to that 5 millimeters that we specified per pass. Then it starts on its second round and it'll make its way from 5 millimeters down to 10 millimeters for the second pass, and now it has to do one final pass to clear up everything at 10 millimeters. So a spiral pass requires an extra rotation or an extra cut around the material to finish off. The better option here is the smooth. Now here we specify a distance over which it will ramp its way down. So I've specified 50 millimeters here. So it will start here, and over a distance of 50 millimeters it'll drop down to my 5 millimeter per pass, then continue its way around at 5 millimeters. And when it gets back to here, it will then spend the next 50 millimeters dropping down to the final depth of 10 millimeters, complete the rotation, and that's it, cut. So the smooth one is the better option here. So let's just calculate this and give it a test. Okay, well that's less than ideal. You can see it's slowing down there as the cutter's dropping. So we're going to come into our CAM software and take a look at its settings. And what we can see here is the feed rate on my Z-axis is at 2,500 millimeters per minute. Now we're running around our X and Y at 7,000, so I'm going to change that to 7,000 and we'll give that a try.
Did you notice the Z-axis as it moved down then? It's only visual, you cannot hear it. It's nice and smooth, it comes around and it starts dropping down over a distance of 50 millimeters. Now you might be saying to me, hey, my Z-axis cannot move that fast. It doesn't need to be. That 7,000 millimeters per minute is twice as fast as my Z-axis will move. But it's not plunging down at that rate. It's plunging down at that rate over a distance of 50 millimeters, and that 50 millimeters may take several seconds to cover, which means that the actual true plunge rate is a lot less. It may be as little as 1,000 millimeters per minute, which is well within the capabilities of my Z-axis. So if you're having trouble using ramps and find that the whole thing's slowing down as you do the ramp and then speeds up again, increase the Z-axis speed and it will probably all come right for you. Now one last thing, and it's to do with feed rate override. I've discovered in my testing here that feed rate override screws up constant velocity settings. What I did is I created a file with a feed rate of 2,300 millimeters per minute. That is 1/3 the speed that all of my other testing has been done. I then ran a feed rate override of 250%, bringing it up to around about 6,500 millimeters per minute, well below what all my other testing has been done at. It would not run smoothly around my oval. I then increased the acceleration by 3 times, and I increased the constant velocity tolerance by a massive 180 units. It still will not run smoothly around that oval. Even though I know for a fact it's well within the capabilities of the machine to do that. So if you're having trouble getting constant velocity working, check that you are not running feed rate override. If you are, set it back to 100%, and if you need to make a speed change, do it in your CAM software. Otherwise, it's likely not to work. So what are the takeaways from this video? Well, first off, my memory is not as good as it used to be. I said in the last video that I used to use exact stop machining rather than constant velocity, and clearly I was wrong. Which more importantly goes to show that you shouldn't take for granted something you see on YouTube, on a forum. If you're not sure about it, question it. Ask the questions and hopefully you'll get the right answers. Next, I do still stand by my analysis that exact stop machining is superior to constant velocity. However, I'm going to modify that. Exact stop machining is superior to constant velocity if your controller is capable of running exact stop properly. Now, my Masso controller is capable of doing that. It can run exact stop without halting and hesitating all over the place. Mach 3 is not capable of doing that, and you need to use constant velocity. So the next thing is, if you're using constant velocity, you have to set it up properly, and those settings are going to be specific to your machine. What I have on mine is very unlikely to suit yours. So that means you need to go through step by step, set it up and test. Once it's all set up, keep testing it intermittently to make sure that it's still correct for what your type of work you're machining. If it's not, make adjustments and keep going. The great thing is you don't actually have to machine anything to do it. you can just simply listen to it as it runs through and see what it sounds like. Also, be aware of the limitations of using constant velocity. Be aware that it will distort your toolpath slightly, and if you're doing something that needs to have sharp corners on it or something like that, you may need to run an exact stop mode. I don't mean you need to run the entire program in exact stop mode. It may be something as simple as just changing the angle at which constant velocity is turned off so it can machine those sharp corners and then continue on using constant velocity. It is a testament to constant velocity that pretty much everything people machine come out all right anyway. But it is something to be aware of. If you're fighting with a problem, just look a little bit deeper. Maybe that is your problem. Maybe constant velocity is causing that last little issue you're having. Next, with constant velocity, acceleration is king. That's a statement one of my subscribers gave, and it's dead right. As we saw there, increasing the acceleration gave much better performance, especially in those corners. So if you can get high acceleration, that's great. Oddly enough, high acceleration is not that good when it comes to exact stop machining, because that high acceleration gives really wicked starts and stops. In exact stop, you don't really need that. A slow acceleration will give a much smoother experience. Next, use your CAM software to produce the best, most efficient, smallest G-code that you can, and you'll get good, smooth results, even with constant velocity turned on. As you saw in that video there, by making changes to the G-code produced, I was able to get that Z-axis to move actually so smooth you didn't even notice it was moving. Lastly, if you're having trouble with your constant velocity setting, check that you're not using feed rate override. Now, it definitely screwed up the settings I have here, but it could be that the settings I'm currently using may just be susceptible to that. Maybe yours are not. But if you are having trouble, try setting your feed rate override back to 100%. It may eliminate the problem that you're having. And that's where I'm going to leave this episode. I hope you've enjoyed it and maybe learned something new. All that remains me to do is to thank you guys for watching. Don't forget to like and subscribe. Leave comments in the comment section below and tell me where I was wrong. And I'll catch you guys later. Cheers.